So I wanted to invite Jesse to come up to speak about the, now I forgot the name of the thing because I got nervous. How to use machine learning for testing and implementing optical networks. Okay, take it away.
Thanks. So I'm Jesse Simsarian from Nokia Bell Labs. I'd like to acknowledge my collaborators in this, Steve Plote, Marina Totten, and Peter Windsor. So I'm going to be speaking about machine learning and optical networks. And so I'm going to be discussing machine learning applications and algorithms. And a big part of this is going to be about a network operating system because we believe that this is necessary in order to have really a dynamic, controllable network that you can run these intelligent algorithms on top of. And a big part of the network operating system will be network abstractions that I'll be discussing. And some, we want to be able to collect data from the network, so I'll be discussing sensors like optical signal-to-noise ratio and fiber polarization sensing, some algorithms like a quality of transmission algorithm that you can use to optimize your network and reduce the margins. And then, of course, you want to take actions, so I'll be showing some error-aware rerouting application and wrap up with some challenges and questions for discussion. So as we see, ubiquitous cloud services will drive bandwidth and dynamism in the network. And we're seeing the situation where compute resources can be instantiated in a matter of minutes, but comparable flexibility is really not possible in the IP optical networks. And there's a number of reasons for this. In your transport networks, you tend to have much more complexity and different vendors, different network elements that you need to be able to control. So we have this situation where the hardware is becoming more flexible. We have FlexGrid ROADMs, flexible bitrate transponders that I'll be discussing, but they're largely quasi-statically configured and not really dynamically configured. So dynamic networking requires a sophisticated network OS to control the network. And we need to manage and allocate resources for optimal network capacity, security, and reliability. And so we need to be able to sense the network and control the optical network. And we can run advanced machine learning algorithms on top of the network OS in order to do the functions that we want. So my main pitch is that the dynamic networking with machine learning requires sensors, abstraction of the network, algorithms, and actuators to actually do something. So fortunately, there's a number of communication industry efforts that are working on software-defined networking for transport networks like the OIF. There's the Open Daylight Controller and the Open Network OS, or ONOS, which is open source NetOS from ON Lab and the Linux Foundation. So the foundations of machine learning applications, underlying the NetOS, we have a flexible tunable network. And here I show the NetOS as being NetUnix, which is a prototype network operating system that we're working on at Bell Labs, and it's based on top of ONOS. And so now we need to be able to get sensor information from the network into the NetOS. And then we want to provide an abstracted view of the network to the algorithms that can run on top. So by abstraction, we want to hide some details of the network, but also present the data that we need in order to run the algorithms on top. So for example, optical margin reduction, we need to be getting some OSNR data and that kind of thing. So we run the algorithms on top, and then actuators actually control the network. And you may have some algorithms that could be running down on the network elements themselves, like a polarization sensor and the OSNR sensor. And I'll be discussing some of that, those functions as I go. So a bit of background about some machine learning algorithms. And this is kind of my fundamental dichotomy of machine learning. On the left side, you see an example of doing numerical optimization. And in this case, I'm thinking about having a model network that you've imposed some physical model on the network, but you maybe don't know all the parameters. And so now you can run machine learning in order to tune those parameters and find out what they are. And just to give a general definition of machine learning, so a computer program is said to learn from experience with respect to some class of tasks and performance measure if the performance of the task as measured by that performance measure improves with experience. So that means you want to have some kind of a training or gaining of experience in order to learn how the system works. And coming back to this example of numerical optimization, I think most people are familiar with this. In this case, you could think of something like an error function, which you're computing something like a signal-to-noise ratio, and you have an error function that is comparing it to the actual signal-to-noise ratio that you measure. And now you want to run some training or optimization in order to tune some parameters in the network. And here I'm showing some animation of a gradient descent algorithm. And you're probably aware of this. With the gradient descent, you can do a derivative of the error function and then basically follow the steepest descent in order to minimize your error function. So in this case, the performance measure is this error function. The class of tasks is that you want to minimize it, and the experience is the trajectories that you take as you vary these parameters. And you can think of it like a ball rolling down a hill and finding the minimum of that error function. So in that case, you had sort of imposed a physical model on your system and you're trying to optimize it. In the other case, you can use something like artificial neural networks. And this has been getting a lot of press recently for some really amazing problems that it's being able to solve. And here you're just kind of using a black box. You don't impose a physical model of your system. You're just basically giving it a neural network that you train from inputs and outputs, and this thing finds the transformation from inputs to outputs. It's pretty easy to describe how one of these neurons works. It's like a neuron in the brain. This artificial neuron has a number of inputs, and these inputs are weighted, and then you do a summation of these weights, and you compare it, you do a threshold function, so some nonlinear transform here. And so if the sum of those weights are above a threshold, then that neuron fires. If it's below the threshold, then it doesn't fire. So it's simple to describe the operation of one of those elements. Now the magic comes in when you combine many of them into a network, and now you've got a function like a brain that can actually learn something. And so now you run an algorithm to find the optimal weights to transform your inputs into the outputs. And here I'm showing an example of something I pulled off the web of a artificial neural network that was trained to complete this Mario level. And what it's doing is it's using an abstracted view of the network. So there's, in that gray box, you see an abstracted view of the playing field. And then these black boxes are the monsters that come through and trigger the artificial neural network to process. And in the end, you have actuation, which is pressing of the buttons. So the way you train these things, you can think of it like the way a child learns language. You don't actually sit down and try to describe to a child, what's a subject, what's a verb, and the structure of language or something like this. You just keep giving it examples. You just talk to the child. You give positive reinforcement, negative reinforcement, and somehow it's able to learn. So it's kind of a black box function, but it's able to produce something useful. So coming back to dynamic and flexible networks, as I mentioned, we have a lot of flexibility coming in on the optical layer. We have flexible client interfaces coming. We have bandwidth variable transponders and channels. We have super channels on the optical layer, multiple optical channels that are bundled together. And we have flex grid ROADMs where you can vary the bandwidth available for these different channels. So there's a lot of sort of free parameters here now that you can tweak, and you need some intelligence in order to be able to make good decisions on how to do that. And the other thing we want to do is improve our sensing capabilities of the network. So if there's some kind of a disturbance or an impairment, like in this case, a backhoe is digging near your fiber network, we want to sense that something is creating a problem, and then you can take some kind of an action if you want to. So in the end, what do we want to do? We want to get the most capacity out of our WDM system as possible. And we're in this interesting situation now with optical networks where we're approaching the fundamental limits of single mode, single channel, fiber capacity. Single mode fiber capacity. And we have, for example, down in the yellow, We have single carrier products that can change bit rate. So we can have 400 gigabit per second, 200, 250, 100 gigabit per second. And you see this trade-off between spectral efficiency and transmission distance. And this can be understood because when you have these 64 QAM, like the 400G, you have this dense constellation of points. As soon as you add some noise into that system, those constellation points start to bump into each other and you can get errors. So as you come down to 100G with QPSK, the constellation points have better spacing, and now you can get your thousands of kilometers of transmission distance. And notice that we're really not far from the record experiments that you see reported at conferences like OFC and ECOC. And that's really not far from the fundamental limits of the nonlinear fiber Shannon capacity limit. One other thing I want to note here is that you can add in one other knob, which is probabilistic shaping. So I show some constellations from a Bell Labs terabit per second field trial. And with probabilistic shaping, you don't use each constellation point with the same probability. You preferably use the innermost constellation points. And this gives you a little bit more spectral efficiency or reach, but it also allows you to really kind of software fine-tune what your spectral efficiency is. So that green line shows how you can really move along that spectral efficiency versus transmission distance using the probabilistic shaping. And so what we want to do is run as close to the Shannon limit as possible, or close to the forward error correction limit. So now back to the network OS, we call it the network brain. You can think of this like a cognitive global network control plane. I don't want you to be confused. This is not a neural network. The NetOS is a complicated, complex Java software with many different modules. It communicates with network elements and gets data. I'll go into more details about the different modules that we have in this piece of software. But what it does is it takes in the application needs like capacity, latency, security, reliability. It takes in the network state, and then it makes decisions to coordinate, schedule, and control the network resources. And looking a little bit more at the functions that the NetOS does, it has arriving intents. So intents are, it's a term taken from ONOS. It's connectivity in the network. And so there's an intent framework, which is drawing from a network resource manager, pulls in network topology information and performance data. And of course, the network, as the state changes, it reports up to these topology databases. And then in the end, it configures the network. And so what you're trying to achieve here is that you can program the network without really knowing the details. Similar to the way a computer operating system controls your PC. When you write some Java program, you're not worried about what type of video card you're using or something like that. So it's hiding those kinds of details. Now, a bit more about this network abstraction and data models. So fortunately, there's also a lot of ongoing work in the industry looking at these kinds of vendor-independent abstract network representations. And this is an important point for the machine learning algorithms, because you really need to know what information is needed to run the algorithms, how many data points are needed. If you're doing something like joint IP optical network grooming and optimization, then you need the IP optical network topology. If you're doing, for example, optical margin reduction, then you need to be getting optical signal to noise ratio data. And so there's various efforts ongoing here, like the IETF has specified the Yang data modeling language for modeling the configuration of network elements. The Open ROADM has defined interoperability specifications for ROADMs and transponders, pluggable optics. And this includes Yang data models for devices and network services. And there was an excellent tutorial yesterday about OpenConfig, and they're publishing Yang data models for optical transport, terminal optics, wavelength routers, and optical amplifiers. And within the ONF, there's OpenFlow, which is a common southbound interface definition for multi-vendor network element control. So one thing that we want to bring to this is something we call NetGraph, and we're putting that into NetUnix, and it doesn't replace any of these other efforts. What it does is it adds an explicit network layering and topology information into the network model. So if you look at transport networks, some people talk about IP over WDM. In fact, it's much more complicated than that. You have multiple layers: IP, MPLS, Ethernet, and then if you add an OTN, you've got many layers there, WDM. So if you don't have a consistent and a traceable description of your network, then you won't be able to run these algorithms on top, and that's what we are achieving with NetGraph. So if you look under the hood of NetGraph, you see that there's various primitives that are defined. We have links, which is like a fiber connection. We have adapters, and the adapters take you from one layer to another. So you need to define the layers in your network up front, define how you can connect, how you do connect these layers together, and then you can do functions like connectivity tracing and making sure that you have a consistent view presentation of your network with all of its layering. So we have implemented NetGraph Manager into NetUnix, and that's the red box that I've circled here. It exists up in the network level granularity of the NetOS. Below that, you have device level granularity, where you have things like flow managers, link managers. Below that, device drivers, so this is your device-specific adapters. And finally, on the bottom, you have protocols that can communicate with the different network elements. So we use OpenFlow for communicating with the SDN switches. We have a REST interface that can communicate with various Nokia network elements, and it can communicate with a Nokia network element proxy. So the proxy does translation to different protocols like SOAP for communication with transport network elements, Telnet SSH, TCP for connection to a photonic cross-connect that we've developed in Bell Labs. So this NetGraph abstracted network representation maps to the network resources, and we can populate network elements into NetUnix and gather statistics using the southbound interface and control the network elements. So now I'm going to move on and talk more about some sensor functions. And first I'll be speaking about the optical signal-to-noise ratio sensor, and then about fiber polarization sensing. So this optical signal-to-noise ratio sensor, this work is done at the Technical University of Denmark. I've referenced a paper here. And they're using an artificial neural network in order to translate from an eye diagram to an OSNR measurement. And the point here is that you don't want to have these expensive optical spectrum analyzers everywhere in your network. If you can just use a single photodiode and capture the eye diagram, then you can measure something like the variance of on that eye diagram, and then figure out how does that variance measure transform into an OSNR. So they did a neural network with one hidden layer here and showing the weights connecting them. Input, again, is the variance and these weights, and then you train it with a number of different measurements. So first you have to do the training from the measured variances to actual measurements of optical signal-to-noise ratio. Once you do the training and these weights are determined, then you can put in some unknown eye diagram and get the optical signal-to-noise ratio out. And over on the right side is showing that the estimated, after the training, the estimated OSNR using that detector corresponds to the actual measured OSNR. And so, again, coming back, this is an example of this kind of black box training that you do. You're not putting in some kind of a model here. You're just putting in a measurable input. The neural network determines how to do the transformation and gives you an output. Now, moving on to using the fiber as a sensor, you have this continental scale, global scale fiber network. And the motivation here is that one of the leading cause of network outages are fiber breaks. And so we're wondering if you can have some indicator as to whether a fiber is about to be broken, like say a backhoe is digging at your fiber and shaking it. When the fiber is shaken, you rotate the polarization of the light on the fiber. And so now if we can build some polarization sensors into the network, you could detect this kind of shaking and possibly take some action or at least know where the problem was going to be. So we have two different methods here. One is doing a span by span, a measurement of the polarization and looking for fast transients. And that gives you localization down to a span level. Alternatively, you could measure the polarization over an entire path in the network. That doesn't give you the same type of localization unless you start correlating it with other paths that have a problem, and then you look at the overlaps, and then you could try to localize where the problem actually is. So we wanted to turn the optical fiber network into a massively distributed motion detector. And so the first method, using the span-by-span monitoring, here we want to use the optical supervisory channel. So the optical supervisory channel, it doesn't carry customer data, it just carries maintenance data for the transmission system. And it's a single polarization signal. And now if that fiber is disturbed, you could see that the OSC channel has rotated. And so we were proposing that you could put in a single polarization beam splitter, look at the two polarization outputs, take the difference of those two, and you'll get some signal that shows that the polarization is rotating. And since it's terminated at each amplifier site, you'll know what span actually has the problem. Now, one issue is this: we want it to be low cost. So this is not a full polarization state monitor. It's just a single component of the polarization. And so we won't get the full reconstruction of the polarization event. But what we want to do is see how well that works. So we took Peter Windsor's toy here from his childhood and just banged the fiber a bit. And we looked at it with a polarization analyzer, so you get the full polarization state reconstruction. And then we put in our low-cost method, which is just looking at one component of the polarization. And so we expect our method is not going to measure as large of a polarization rotation as the full characterization. And so we did some statistics on it with 58 impacts at different points, different polarization states, and we define a figure of merit that compares our sort of low-cost measurement to a full reconstruction. And we find that it's about 60%. It measures on average about 60% our method compared to the full reconstruction. And so 90% of the measurements had a fidelity greater than 0.25. So it gives some indication that there's some activity happening on your fiber. And then the other method, this was done by my colleagues in France. They looked at the polarization path monitoring. So here you don't need to add in any extra hardware. They're just using the coherent receiver of the dual polarization system. So with these coherent dual polarization systems, you need to track the incoming polarization state of the signal in order to be able to detect both of those polarization states. So they use the Stokes parameters that describes the polarization that comes out of that digital signal processor at the receiver, out of the FPGA, evaluate the polarization rotation speed, and if it's rotating fast enough, if it's above a threshold, then you can record the Stokes trace, and then they did some machine learning in order to classify the event. So here's an example of an event of, say the fiber being hit over on the lower left there. And they have this robot that can do different things like bend the fiber, shake the fiber, hit it, or move it up and down. So these are different events that then they do a machine learning to do the event classification. So collect many thousands of these events for different polarization states. And now you need to define some variables that go into the machine learning, and now you train it on those variables. And you have this event classification function which will find the function that transforms some variables. So the variables are something like one of those polarization Stokes parameters over some period of time transforms those measurements into these events that they could classify. And so what they found was they needed 18 different variables in order to do the event classification with 95% fidelity. And then once you do the event classification, you can say, well, is it a risky event? And if so, you can send an alarm to the controller. Now I'm going to discuss more about the quality of transmission algorithms and the procedure that you can use to do quality of transmission estimation and optimization for margin reduction. So coming back to this question, like why and when do we actually need to learn from experience as opposed to knowing what we're doing? Well, as engineers, we tend to want to make some kind of model of the underlying physics and then predict physical layer performance using that model. But how good is that model? Well, you can introduce this hybrid approach, and that's what I was discussing earlier with the error function and using the machine learning and the gradient descent, where you have a physical model and then you have some parameters that you want to fine-tune using the machine learning. And here the problem at hand, again coming back to we want to squeeze the most capacity out of our optical transport system. And so you need to have an accurate prediction of what's the quality of your transmission, what's the signal to noise ratio that you would expect for that link. If you don't do a very good job of predicting, how that what the quality of that link will be, then you have a lot of spread in your predicted performance versus the actual performance. And to count for that spread, you have to do add in a margin. So the margin is basically some distance away from the forward error correction threshold, and you need to build into that your system. You have to build in this margin in order to account for that spread. But now if you can improve your model and tune the parameters in your model, you can reduce the spread of the actual and the predicted performance. And now if you can do a perfect job and use supervised learning and feedback in the system, then you can match your predicted and your actual performance, and you can run with a low margin and close to the FEC threshold. So we're really talking about optimizing our system, squeezing dBs out of it. And every dB that you have in this planning accuracy is as valuable as a dB encoding gain. So it is important. So if we look at the optical system margin reduction, this is also work done by Bell Labs colleagues in France. So they used a learning process to reduce those uncertainties in the quality of transmission estimation. In the upper left-hand corner, it shows the life cycle of deploying connections or wavelengths in the network. You have your initial deployment, which is using a planning tool that is not very accurate, say, and so you have to put a fairly large margin in, at least initially. And then as you add demands into the system, you can start doing the training and improve the accuracy of your parameters. So for example, the parameters in this model would be the noise figures of your amplifiers and the power going into different amplifiers. So ahead of time you wouldn't know what all those values are, but now you do a training on it. The learning algorithm is shown in the upper right. Start with some values of the input parameters that you expect. Make a cost function, which is comparing the calculated signal to noise ratio versus the actual measured values that you get in the network. And now you can do a gradient descent algorithm as described earlier to modify those parameters. And when you find that it converges, you have a little error, that now you've got new values of the parameters, and subsequent demands coming in can now have much lower margin. So that's being shown over in the lower left-hand corner, where this is a simulated system of a European backbone network. And what they've done is add demands into the system and then start doing training on it. So without the learning, you have the red curve, which shows a fairly large spread in the predicted versus actual OSNR values. So you have like plus or minus 1 dB that you would have to build in for margin there. Now, once you do the learning, you reduce the uncertainty in that signal-to-noise ratio prediction, and then you can get down to 1/10 of a dB. And so that basically means you understand how that network is operating, what the different contributions are from the different amplifiers, and you can operate very close to the FEC limit. In the lower right, you see different graphs that show different starting conditions, like say you have some systematic error in your power measurement or systematic error in your noise figure estimation. But as you add more demands and wavelengths into the system, then that uncertainty reduces, so the SNR error after 600 wavelengths being deployed with the training gets down to like 0.1 dB. So now I'm going to discuss a bit about action. So we want to actually do something with all of this data and algorithms that we've collected. And for that, we have SDN testbed in New Jersey, where we have different locations throughout the building. We have a bunch of servers that can run applications. We have a photonic cross-connect, which is a prototype MEMS switch that is under development. And then we have connectivity to another area where we have service routers and optical transport and SDN switches. And now we can demonstrate these kinds of applications running on a network. This is the demonstration of error-aware rerouting. So I'm showing the front panel GUI of NetUnix, and you see 3 switches on top and 3 transport boxes below. So the switches are on the packet layer, obviously with electronic switching, and the optical transport is a WDM system. So you see the blue lines are discovered connections on the packet level from the NetOS. Those logically they're on the packet level interconnections, but physically each connection actually goes down to the optical layer through the WDM system and back up again. And so now we use NetGraph, which describes the layering in the network, to make the associations between links on the packet layer and links on the optical layer. I started out by setting up 2 intents in the network between host 1 and 2 is an error-aware intent. Between host 3 and 4 is a regular intent. So with the regular intent, it won't respond to any error condition or any condition on the optical layer unless the link fails. In the case of the error-aware intent, we can program it so that if you have a high error condition, you could do prefec or postfec condition on the optical layer, then you can take some action on the packet layer. And that's what's shown down below. So I've actually injected errors by turning the light on and off on the optical layer. So I've made postfec errors in this case. And you see a yellow triangle showing that there was a high error condition. And the regular intent stays on the initial path. So even though there's postfec errors, it's still staying on the initial path. It could be that there's some tolerance in that by using TCP, and that's some things we've looked at. The error-aware intent is not tolerant to these kinds of errors, and so it's been rerouted on the IP layer in response to something happening on the optical layer. So coming back to our challenges and discussion points for network operators, so you all in the room, so we can have some discussion. So what kinds of, obviously you want to have a stable and reliable network. And, as I mentioned earlier in the talk, we did some event classification and had a 95%, accuracy in the event classification. There's this question of, how much certainty do you need for it to be useful? here's another example where the experimenters were classifying a different modulation format and getting like 96% accuracy, 87% accuracy. How much accuracy is required? And how much data do you need? So coming back to this question of abstraction, so how much data is enough for the basis of machine learning? So what data is needed at which layer of the network? So some of your machine learning algorithms could be running down locally on the network element, like the sensor data, the OSNR, and the polarization sensing, whereas other algorithms would run on top of your network OS, more network-wide, rerouting or optimization algorithms. And so where do you need to bring the data in, and where does it need to be presented? And then, of course, there's reliability and operational implications to having this kind of dynamism in the network. When does human operator confirmation need to come in for these different network operations, like a reroute condition? And with some operators, I assume there's some business structures, like differences between IP and optical businesses, that these kind of operational barriers to bringing this kind of dynamism in that may have nothing to do with technical, but everything to do with how businesses are structured. And then, of course, there's a question of outages and accountability. So if there's an outage, was it the problem of the machine learning algorithm running on top of the network operating system, or was there some faulty data that was collected? And these things would need to be debugged and understood. So in conclusion, we see cloud services driving bandwidth and network dynamism. And the main point is that to have these really dynamic networks with machine learning, you would need to have sensors, some proper abstraction algorithms that run on top, and actuators. And so the machine learning algorithms I showed can be used to identify network events, reduce optical system margin, optimize the network, and it can be built on top of a programmable NetOS with flexible network infrastructure. And I talked about this dichotomy of the different machine learning methods, ranging from kind of a black box artificial neural network to event classification, to these hybrid methods that could use a physical model of the system and machine learning to optimize that model. And we've been working on the NetUnix prototype NetOS to improve the sensing of the physical layer and represent the network using NetGraph. And I showed some application of impairment-aware rerouting. So thank you for your attention.
Question? I'm here. So I have a question here. Why do you choose artificial neural networks? Just because your data set derived out of sensors is linearly non-separable? And how do you even found out like it is linearly non-separable in the first place? And I have a second question on event classification. Again, is that on neural networks, or have you tried any other classifiers?
Sorry, what's the second question again?
On your event classification.
Yeah.
Okay, is it neural networks, or have you explored any other classifiers?
Okay, so I'm going to come back to, I believe you're talking about these experiments?
Yes.
Yeah, so this was, right, it was using this naive Bayesian classification where you're assuming that there's independence among these different events. So I haven't explored whether that independence is actually true or not, but in fact it's able to do the classification. So with these tests, you're kind of making an assumption and seeing how well it works. So it is kind of this black box that you're not sure exactly how it's working, but it's doing the job for you. And then the second question, I'm sorry, there was about...
on the neural networks, and just because you chose it is the data derived out of sensors is linearly non-separable, right? So artificial intelligence or artificial neural networks could be used when the data is linearly non-separable. My question is, how do we even figure out the data that you derived out of the sensors is linearly non-separable in the first place?
Yeah, no, it's a good question, and it's a bit of a trial and error thing that going for a good result, and you know, I'm afraid I don't have a kind of quantitative response for you, but it's more like trying out the algorithms and seeing what kind of a response you get.
Thanks.
Matt Petak, Yahoo. I love what you're doing here. I think one of the interesting challenges when you talk about machine learning is an inherent train and then here's my training set. Okay, now here's my ongoing actual data being fed into it. Assumes to a large degree that once the training period is over, that the model is set and static. And I think as network engineers, everyone in the room understands that your network is never static.
Right.
The data you trained it on last week is no longer really the reality. There are degradations in patch panels, people bump against connectors. Have you thought about how you would do a model in which you have essentially simultaneous, I learned yesterday and the day before and the day before that, and I am evaluating my current day against it. But at the same time, the world is different today than it was yesterday. So I'm also simultaneously having to learn what is the new state of the world. That trade-off, I think, is one that machine learning still hasn't bridged yet.
Yeah. No, it's a good point. And so, I think it's applicable to these kinds of experiments here, where you have your initial deployment, then you have in the life cycle this retraining, which is shown there, and it's shown like a feedback loop that's never ending. And so now, in some sense, you're expecting that the system is not going to be so incredibly perturbed at some point that it's going to completely fly off the rails. But I think there's a lot of work that would need to go into see what happens. Somebody unplugs a fiber, rubs it with their finger, plugs it back in. Now you've got a signal-to-noise ratio in the network that has vastly changed. And so now the system is going to converge to some new value. So that's kind of like a dynamic study that you could do with this kind of a model network, assuming some topology, and now throw in some huge loss somewhere, and see what happens. How much do you perturb it? It's an interesting dynamic study, I think. Yeah.
Cool, thank you.
Hi, Jeff and Sarah. Great presentation, great slides. Question, somewhere in your slides you had magic word multi-layer. So the question, how do you normalize data across layers? And you've got service, packet, and optical layer with very different set of inputs and life cycles. How do you do this?
So how do you normalize the data across layers, you asked?
Yeah, dynamics in packet are very different than dynamics in optical networks, and
Yes.
have different meanings.
Yes, that's very true. So, that will definitely have to be taken into account. So, the rerouting experiments that I showed here, the sensing was being done at the optical layer, and the rerouting was happening at the packet layer. So, there wasn't kind of a complex interplay between the different time scales of the different layers. So, you make a good point that the optical rerouting, if you're really setting up a new connection on the optical layer, it can take a lot more time than rerouting at the packet layer. So now, you're going to have to take that into consideration. Here, I sort of got rid of that problem by just doing the rerouting at the packet layer and collecting data from the optical layer. But in the future, you'll have to deal with these different time scales. Yeah.
Have you looked into recursiveness when you have all three layers together and what it takes actually to compute it?
No, we haven't looked at that.
Thank you.
Hello.
Oh, do you have one more? Oh, there we go.
Hi, Chris Spears, Facebook. So what method of interaction did you have to actually get the sensors to determine PMD information, for example? And how does that tie into the predictive ability of the model to predict that you have the ground shaking, that you're about to have a fiber cut, for example?
Okay, so this is for the polarization sensing. You are back here. Sorry, can you repeat?
So if you rely on like streaming telemetry or just occasional TL1 polling or some other RPC method,
Yeah.
And you get that data, and how predictive can you actually be off of that? So do you sense that the ground is shaking versus the ground is already, been moved and the fiber cable has actually been shunted and like you're about to be cut, or you just were cut already? How predictive can you actually be versus, so there's a balance always of, can we be predictive about something, or can we be quickly reactive to something? And how you're measuring this is going to determine also how quickly you can react if it is a predictive event, because you have to get the data into your model, then you have to look at it, then you have to analyze it, and you say, well, this is something I can act on. Can my systems to react at the upper layers actually do something in that amount of time?
Yeah, definitely. Those are all good points. Again, coming back to the question of time scale, and now what action do you actually want to take? How long does it take to do the classification, and how proactive do you want to be? How much time do you have to be proactive? Unfortunately, I don't have any data that's coming from the field showing these kinds of cut events, and that's sort of an open invitation to anybody here if you want to collaborate on looking at, what are the timescales involved in seeing some kind of polarization signal happening on the fiber, before a cut. So how much time do you actually have to make a decision? So we haven't really, pushed that angle because we're lacking in data as to, how much time do you have, what's typical, how do these things actually behave in the field when you have a disturbance like that? So we haven't really delved into timescale for reaction yet. Yeah.
Cool. And what open APIs are you using to operate or interact with your optical systems?
I'm sorry, can you please?
What open APIs are you using to operate your optical systems?
So for the optical system, I showed. So we're using a southbound interface that we we made ourselves this REST interface that can populate devices into the NetOS, and then it has a translation to, whatever type of device we want, Telnet, SSH, SOAP, or TCP.
Wouldn't it be great if all the optical vendors adopted open APIs?
So we don't, there's a SOAP interface on the network management to go to the transport, but we're basically doing our own thing here.
Cool. Thanks.
All right. Thanks again.
Thank you very much, Jesse. We appreciate that.